All right, the next problem is number 35, and we're looking for the empirical formula of a compound, and here are the percentages. So the first thing that we're going to do is we're going to add up the percentages. Go ahead and add 30 and 69. So this is very close to 70. This is very close to 30. But go ahead and add them up into the calculator and verify that it is equal to 100. And so I've already done that. And so 30 plus 69 is 99. 0.6 and 0.4 is the 1%, which is the 100. So if we add them, it is 100. So if we're able to do that, the one thing that we can do is we can change the percent sign to grams. And so I'm going to go ahead and do that now. Now, what I want to do is I'm going to bring these masses from over here on the far right. I'm going to bring them over here because we're going to do some work. We're trying to figure out the empirical formula. What you need is the steps. So remember, the steps were provided in your notes. I'm going to go ahead and provide the steps here verbally, but follow along. And so what I will do is I will show you the work incrementally and explain as I go. So the very first thing that I'm going to do is I'm going to go ahead and divide both of these values by the molar mass of nitrogen for the top number and by the molar mass of oxygen for the bottom number. I'm going to go ahead and put that in blue. So when we do that, what's going to happen here is the unit of grams is going to cancel, leaving you only moles. So the number that we get here in red is going to be the mole number for nitrogen and in oxygen. Let me go ahead and put that there. So now I've got the number of moles. The next step is to look at both of these numbers and look at and ask which one's smaller, 2.171 or 4.35. Clearly, the 2.17 is smaller, so I'm going to take this number and divide both of these numbers in red by 2.171 because it's the smaller one. I'm going to go ahead and put that in green. So now, the resulting number is going to be that we have one nitrogen atom in the formula, and we've got 2.003 oxygen atoms in the formula. 2.003 is very close to a 2. So we're going to do that, and the 1 is a whole number. What we're trying to do here in the green section is we want to make sure that we have whole numbers. So if you have a number that's like 2.5, you want to make sure you multiply that by 2. If it's 2.25, multiply by 4. Or if it's any other number, you want to make sure that you ultimately get a whole number, so you might want to multiply by a multiple until you reach that whole number. Now that we've got whole numbers here, 1 and 2, we want to make sure that we put the more electronegative atom last. Oxygen is electronegative, more electronegative compared to nitrogen. So oxygen will be last. And so what we'll do here, just to translate the subscript here, we're going to put nitrogen, but the subscript is a 1. So we'll put that as a 1 like that, and we'll translate this one here. We've got an oxygen with a subscript of a 2. So here, oxygen with a subscript 2. And if we put them in the formula, that formula, we don't need to write the 1s, but the formula would be NO2. This formula corresponds to the empirical formula for this particular problem. So let's go ahead and go on to problem number 36. 36 is asking us to find the molecular formula of a compound that has a molecular mass of 42, and we've got an empirical. So if we cut down to the thing that we're going to figure out here, we're going to get the molecular mass, or the molecular formula mass, and we're going to divide that by the empirical formula mass so that we can figure out the multiplier. Notice in the problem there is no empirical formula mass, but they do give us an empirical formula, so we need to come up with a mass of this compound here quickly. So if we do that really quick here, carbon is 12, hydrogen is 1, there's 2 copies, we add that up, so this is 12 plus 2, which gives us a mass of 14. This is the empirical formula mass. So if I come over here and enter that information over here in the formula that I've already written down, I've got 14 grams per mole for that compound for the empirical. And now I'm going to get the molecular formula mass, which is provided right here, which is 42. So I take 42 in the numerator, grams per mole. The units are going to cancel entirely, and our multiplier is going to be the following. Go ahead and take 42 divided by 14. That'll give you a multiplier of 3. So here is the multiplier. Now, what do we do with the multiplier? Well, what we're going to do with the multiplier is we're going to get the empirical formula. That empirical formula was provided for us in the problem over here, CH2. So let's start there, CH2. And now this multiplier, let's put this in purple so we can kind of color code everything. And there's already a default 1 here. I'll just put it there just for reference. But we're going to take the multiplier from this area and we're going to multiply each of the subscripts in the empirical. So we're going to say here times 3 and times 3. And if we translate this, the 1 times 3 will give you a carbon to the third power. And if we take the 2 times 3 is going to be 6. So we'll write a hydrogen and a 6. So this here, this is the molecular formula in purple. Okay, let's move on to problem number 37. And so that problem, we'll bring it up to the top. Here we're looking for the reactivity of potassium compared to calcium, and we want to explain this based on the number of valence electrons and how it influences behavior. Well, the reactivity is going to be based on or referring to how quickly or how easily is it going to react with another element. Well, the one thing that we know for sure is that potassium is going to be in group 1, whereas calcium is in group 2. Being in group 1, that means that you're going to have 1 valence electron for the potassium, and for the calcium, that means that you're going to have 2 valence electrons. Now, when you look at these numbers here, these numbers are going to tell you quite a bit. The 1 valence electron means that it lost 1 electron because it was able to get to the octet in the lower orbital a lot sooner. It's a lot easier to lose 1 electron than it is to lose 2 electrons. So compared to both of these, potassium would probably have a lot easier time reacting with another element because it's a lot easier to lose this 1 electron. So if I'm predicting the reactivity, I would say that potassium is going to be way more reactive. So I would say that this particular element here is going to be more reactive. And the main reason is because it's got 1 valence electron compared to the calcium. And 1 valence electron is a lot easier to lose than 2. And that's definitely going to influence the behavior of the reactivity. Okay. And finally, we've come to the last question of the review. Let's get this up to the top. So the final question asks us to describe the type of bonds formed when reactive metal atoms from group 1 or group 2 bond with nonmetals in group 17. So let's just kind of bring a list of elements in group 17 and then put them over here on the side so we have some reference. And then we're going to go ahead and name the type of bond that these atoms commonly form and explain why these atoms tend to form this type of bond. So I'll give you a little bit of a clue. The reason has a lot to do with the electronegativity. So we're going to have to look at some electronegativity values. That'll probably be the easiest. Instead of writing them on the side, let me just bring the table up and then you'll get to see what I'm talking about. All right, so here are the elements. And so let me move this down a little bit so you can see the actual question. Here are the types of bonds that are going to be formed when group 1 elements. So here we got these group 1 elements. Take a look at the numbers. They're really low. 0.98 for lithium, 0.82 for rubidium, 0.7 for francium, and similar numbers here for group 2 elements beginning with beryllium. So they're going to be grouping with group 17, which are going to be these elements over here. Let me change the color on this pointer. So that's going to be over here with fluorine. And then look at the number, 3.96 or 98, 3.16 for the chlorine, and even for iodine is 2.86. So the numbers are pretty big. So the type of bond that forms, because there's a huge difference here, the type of bonds that are going to be formed literally here are going to be ionic. Now, how do we get that? Well, what we're going to do here is do something known as the electronegativity difference. And the main thing here is if this difference is greater than 1.8, that's definitely going to be an ionic. Okay? And so let's take a look at this. So let's just take an example here. If we take, for example, take a lithium and let's combine it with fluorine. So the lithium, and let's use this here, the lithium is going to have an electronegativity value of 0.96, and the fluorine is equal to an electronegativity value of 3.98. So what I'm going to do here is I'm going to subtract, but I'm going to use the bigger number. So here I'm going to take 3.98 minus 0.96. That gives us a 2 overall. And so if we look at that, notice the huge number. 3.02 is significantly greater than 1.8. So the bond that forms between lithium and fluorine, this is definitely going to be an ionic. All right. And so that's the kind of bond that's going to form with a lot of these atoms here in the first group or the second group when they combine with group 17 elements. Now, one thing to note, even though the question's not asking us, just to point out, as the element that we're getting gets closer to the nonmetals, the difference in the electronegativity is going to go down. And so if this difference goes below 1.8, then at that point it becomes covalent. But it's going to be polar covalent if it's less than 1.8. And as long as it's above 0.3, then it will be polar. But once the difference falls below 0.3, then it becomes nonpolar. So anyway, that is the review for the semester exam. You want to continue reviewing on your own. Do the best you can. If you have any questions, see me in class. Have a great one, everybody.